Or maybe we'll have a synthesis quiz, I don't know. See how far we get. So what we want to talk about now is synthesis of aromatic compounds. How can I put a set of substituents in desired locations on a benzene ring? So let's say I start with benzene, right? That's the usual starting material. And what I want is orthobromoanisole, or 2-bromoanisole. And the question is, what series of reactions are going to allow me to make that desired compound, 2-bromoanisole, starting with benzene? We already know that if we actually had anisole and we did the bromine reaction on it, the bromination, the major product would be not 2-bromoanisole, but 4-bromoanisole. Right? So that's problematic, right? Because we want the bromine in the 2 position. So the first thing we have to decide is what group are we going to put on there first? Are we going to put the bromine on first and then worry about the methoxy group? Or are we going to put the methoxy group on there first and then worry about the bromine? Bromine is an orthoparadirector, as is the methoxy group. But bromine is a deactivating substituent, whereas the methoxy group is an activating substituent. So it might make sense to put the methoxy group in there first, and then the bromine. But if we do that, we're going to have to overcome this problem, which causes the bromine to be directed to the para position, because inductively the methoxy group is deactivating the ortho position. There is a way around that. We can block this temporarily and then take that blocking group off. So if we had anisole and we wanted to make 4-bromo or 2-bromoanisole, we would first need to basically protect the 4 position so it's not available. So how do we do that? Or in other words, what groups are available to you that can be taken back off again afterwards? And one of those is the SO3 group. Because in fuming sulfuric acid, you can put an SO3 group on, and in dilute sulfuric acid, you can heat it up and take it back off. If we were to react this with fuming sulfuric acid, the preferred position of attack would be in that 4 position, because that resonance structure allows the positive charge to go next to the methoxy group, and it's further away from the methoxy group for inductive effect. So for exactly the same reason that this is selected for the para position, this one is also selected for the para position. Right? Any electrophilic aromatic substitution reaction on methoxybenzene or anisole is going to go to the para position first. Now, this is an OP director, and this is a meta-director. So they're actually both activating the same positions on the ring. That's a good thing. If they're in conflict, the more activating substituent is the one that wins. Right? So if there's an argument between methoxy and sulfonic acid as to which position they want, methoxy, because it's an activating substituent, wins. Remember that the sulfonic acid is actually deactivating the entire ring. It's just deactivating these positions more strongly than it deactivates those positions. Right? So it's not really activating the meta positions. It's just not deactivating them as much. Right? If you're actually activating a position, right, you get your way. Right? Activating is better than not deactivating. So now we can do the bromination reaction. Bromine will actually go where we want it, in the ortho position. We don't generally have to worry about overbromination as long as we use one equivalent. Because remember that that's also a deactivating substituent. Which means that the product is less reactive than the starting material. Does that make sense? Generally, it's possible to stop when the product of the reaction is less reactive to the reaction conditions than the starting material. If the product is more reactive, it's difficult to stop, and that's why we have to worry about over-alkylation when we have an alkyl group, because the next substituent on actually activates the ring. It is possible to do another bromination if you use excess Br2 and you heat it up. But where would it go? Because now this is an ortho-para director that wants it here. But this is also an ortho-para director, and that wants it here, or here. So who wins, methoxy or bromo, if they're in competition as they are in this case? Sulfonic acid gets no say, right, because that's a strongly deactivating substituent by resin. The sulfonic acid actually kind of wants it here, but nobody's really listening to the sulfonic acid. The methoxy wins. Why? Because it's the more powerful activator, right? Bromine's a deactivating substituent. It's an ortho-para director, but not, right, inductively. So the bromine would go here if another one went there. You do have two groups saying that you want it there, as opposed to the one group that's saying that it should go here. But the most important factor is this is the more strongly activating substituent. Methoxy would also win over like an amido group, right, because it's more powerful. So now we have that bromine there, which is where we want it. We've got to take that group off. And the way to take that group off is to react it with dilute sulfuric acid. Water, sulfuric acid, a little bit of heat, and that's going to take that group off. How does that work? What's the mechanism for removing that sulfonic acid? So we've got a protection, right? Block the para position. Then we have the reaction to put the bromine on, and now we're going to basically protect or deblock that sulfonic acid group. So we've actually just changed the problem, right? From how to make 2-bromoanisole to how to make anisole in the first place. Once we have anisole, we know that we can put this bromine in the 2 position by blocking the 4 position, brominating, and then unblocking. What's the mechanism for this reaction? ask for that mechanism. It's actually kind of irrelevant that the bromine and the OCH3 group are on there from the blocking position. So this is what's in solution. What would you do? Let's take a look at the forward reaction. What was the next step of the forward reaction? Eliminate that. And then the last step, take that hydrogen off using either HSO4 minus or water to take that and generate the product. This is an equilibrium reaction. As such, the principle of microscopic reversibility applies, and the reverse reaction has to go through exactly the same set of intermediates as the forward reaction, right? Because the energy drawing is going to be the same in both directions. So that tells me that that is going to be an intermediate of the deblocking procedure. Since the last step of the forward reaction was to take the proton off the benzene ring, the first step of the reverse reaction is going to be to put that proton on. To generate this intermediate. And it likes this intermediate, right, because there's a resonance structure that puts the positive charge on that carbon that's attached to the methoxy group. So that's a favorable position of attack. So now what? What's the next step? Well, we have to go through this intermediate. So the next step has to be to remove that proton. Now the sulfur trioxide can spontaneously fall off. To regenerate the aromaticity. But that's still an equilibrium reaction. So why does the equilibrium lie towards the unsubstituted benzene in the case of dilute sulfuric acid, whereas in fuming sulfuric acid, the equilibrium lies towards the SO3H group being attached to the benzene ring. The reason is because sulfur trioxide reacts very quickly with water. Remember, that's the reason why acid rain exists. Sulfur trioxide in the atmosphere reacts with moisture in the atmosphere to form H2SO4. 2 proton transfer steps, now putting a proton off on that, and then taking the proton off the other hydrogen on the OH2 group is going to form sulfuric acid. So the driving force, this is an irreversible step. Drives that equilibrium by removing the product, right? One of the products of this reverse reaction is SO3. If you can remove that SO3 from solution as it's formed, Le Chatelet's principle will take care of the rest and will drive the equilibrium forward to produce more SO3. So it's the water that's the key here. The presence of the water, which is not present in fuming sulfuric acid, causes that SO3 to be no longer available for being attacked by the benzene ring. So we can reversibly block the para position anytime we want by sulfonating and then desulfonating with dilute sulfuric acid. So how are we going to make anisole in the first place? How do we do this first step to create methoxybenzene from benzene? So we've got to put an oxygen onto the ring, right? Can we generate an oxygen cation, O+? No, right? We're not going to be able to put that methoxy group in there directly by creating CH3O+. There is no such thing as CH3O+. So if we're working backwards from methoxybenzene, in a retrosynthesis, we can certainly create methoxybenzene or anisole from phenol. It would be fairly straightforward. All we would have to do is take that proton off, and it's relatively acidic. pKa of phenol is around 10, so we can use a relatively weak base to take that off. We could probably actually just use potassium carbonate or even potassium bicarbonate. And then the phenoxide ion would be very good as a nucleophile to attack methyl iodide. So mechanistically it would look like this. Bicarbonate ion would take that proton off. Beautiful SN2 reaction. So then the question is, how do we make phenol? How do we put an OH group on there? We can't have OH plus any more than we can have OCH3 plus. So how do we introduce an oxygen onto the ring in the first place? So you want to try to do a Friedel-Crafts reaction using this? And then activate that. That would be making basically OCH3+, but it would be making it in masked form.
No, I missed.
You do know how to put a phenol on there.
Can you do it through a cyanide something?
You know that you can make a phenol from an NH2 group by diazotizing it. If we treat this with HNO2, right, which we normally make by mixing NaNO2 with HCl, we will make the diazonium salt. And then that diazonium salt reacts with water. It may just fall off to form a positively charged ring, which can then get attacked by water. Because N2 gas is an excellent leaving group. So it may just fall off, or it may be that water attacks first, and then the nitrogen falls off. Right? Because you can imagine that with that powerful electron withdrawing group here, this position could be subject to nucleophilic attack. So water could come in and do this. And then that would come back in and kick off nitrogen. So whether this is a discrete intermediate or whether it's a couple of steps, either way, you're going to generate this. And that's going to make the phenol. So you don't really even need a two-step reaction here. If you mix together sodium nitrate aqueous HCl, you're going to get the phenol from the NH2 group. You can convert that NH2 group into the diazonium salt, and then in the second step, put lots of other things in, right? So there are many things that you can convert that diazonium salt to, but in this case, we're just trying to get it attacked by water, which is probably the solvent anyway for the sodium nitrate and the HCl. That's a nice reaction. It goes well. So now the problem is how to make this. If we have this, we're good, right? We can diazotize it in the presence of water to make the phenol, and then we can do this reaction to put the CH3 group on there, and we're in business. So how do we make aminobenzene, or aniline, from benzene? So we keep simplifying the problem. We started with the problem of how to make ortho-bromoanisole, then we simplified it to, okay, how do we make anisole? And now we've simplified it to, okay, how do we make aniline?
Well, first you're going to have to make an NO2 group and then change the NO2 group to NH2.
And you always have to make a nitro group first. You can't put an NH2 plus group on. So anytime you want an NH2 group on the ring, it started out life as an NO2 group. And there are various ways that you can do that, including the Clemenson reduction with zinc amalgam in the presence of HCl. So now we have the whole synthesis. Right? If we wanted to, we could write the whole synthesis out. HNO3, 71%. H2SO4, 98%. That makes nitrobenzene. any of the various methods. Iron and HCl would be another way. Ready nickel and H2 gas would be another way. Diazotization to make the phenol. Put a methoxy group on there. SO3 gas, H2SO4 liquid, fuming sulfuric acid. Put the sulfonic acid in the 4 position. Brominate. And finally, sulfuric acid to take that off. So it's a 7-step process to make it. Nitrate, reduce, diazotize, SN2, sulfonate to block the 4 position, brominate, and then unblocks the 4 position. Is there a reason why we couldn't have just taken phenol? Put the bromine in there? Or alternatively, taken phenol and treated that with SO3 and H2SO4? Did we have to make it into a methoxy group before we could go any further? If you were to do this, phenol is a very strongly activating group. You don't actually even need the FeBr3. Phenol is a strong enough activating group that you can brominate it directly with bromine. So there's no way that you're going to stop overbromination of the phenol. The OCH3 group is less reactive than the phenol. And in fact, protection by turning the phenol into the methoxy group, followed by taking that group back off, is a way to make that phenol not cause overreaction. So if we wanted to make this product, and we wanted to avoid that, we would in fact protect it as the methoxy group, and then brominate it, and then we would take the methoxy group back off. And if you want to take the methoxy group back off, you use concentrated HI. So that's a way of protecting that group to reduce the reactivity. Concentrated aqueous HI converts that back to the phenol and gives you CH3I as a product. You can think about that mechanism, but it's another SN2 pathway. So we can't do that, plus we don't really want that. Can we selectively put an SO3H group on the para position and then brominate? Well, again, OH is a strong enough group that we're probably going to brominate in both locations, but besides, you couldn't do this. Why can you not sulfonate phenol very easily? Remember how vigorously SO3 reacted with water? SO3 is smart enough to tell the difference between this lone pair and that lone pair? No. It's going to see that lone pair, and all you're going to do is react the OH group with the sulfonic acid. Right? You're not going to get the ring to react with the sulfonic acid because these pairs of electrons are much more nucleophilic. So it's not possible to directly sulfonate phenol. If you want a sulfonate group and a phenol, right, the sulfonate group has to be there before you introduce the phenol. So it is actually essential in this case to make the methoxy group, make anisole first, and then do your reversible blocking and bromination, rather than trying to proceed directly from phenol and do your blocking and bromination and then put the methoxy group in the last step. That won't work. There's often syntheses where there's two different routes, and one route will work and the other one won't. Let's take a break, and then we will do another couple of syntheses